In this video of our series on discrete time signals, we will be discussing elementary discrete time, or DT signals. Now, one of the reasons that we wanted to discuss elementary signals or functions is because they are used to represent much more complicated signals. So the major benefit of representing discrete signals or continuous signals in terms of elementary functions is that it simplifies the analysis and design of linear systems. So the first elementary signal or function that we will discuss is the unit step function. Now, the unit step function is one of the most simple of the elementary signals, and it is as simple as writing u of k equals 1 when k is greater than or equal to 0, and 0 when k is less than 0. Now, the plot for this is very simple. So we're going to plot it from -4 to 4. So for all negative values, u of k will equal 0. But once we hit 0, u of k will equal 1 for all of the positive values. Always remember that when you're drawing a plot for a discrete signal, do not make it look like a continuous signal. So it should look like a stem plot almost. Now, along with this video, I have included a MATLAB supplement that includes the M files for each of the elementary signals that will be discussed in this video. And during this video, I will show you the M file and also the plot that was generated from the M file. Now, for the unit step, on the left you should see the M file code, and on the right should be the plot. Now, the plot looks pretty much exactly like what we plotted before.
Now, found on the left here is the M file for the unit step function, and on the right is the plot that was generated from the code. Now, the M file for the unit step function is fairly simple. It's fairly similar to plotting the unit step function as a continuous signal. The only difference is that you use stem when you plot the signal instead of just using the MATLAB instruction plot. Other than that, the code is pretty basic by using the built-in unit step function in MATLAB. And the plot that is generated from this was very similar to the plot that we just made previously.
Now, the next elementary signal that will be discussed is the rectangular pulse. Now, the rectangular pulse is a fairly simple elementary signals, but in all honesty, most of them are fairly simple, which is why we use them. So the rectangular pulse is written as rect k over 2n plus 1, and it equals 1 when the absolute value of k is less than or equal to n, and 0 when the absolute value of k is greater than n. So for the rectangular pulse, it's basically just a pulse, and it depends on the value of n. The value of n is basically the width for that pulse, and everywhere else outside of that width is 0. So this is a basic plot for a rectangular pulse. So it depends primarily on n. So if we say that n is right here, and we say that negative n is right here, and everywhere else is 0. And only within the width of the pulse does the rect function equal 1. Now, the MATLAB code for this function can be seen on the left, and the plot that's generated can be seen on the right. Now, just like the unit step, the MATLAB code is relatively similar to the MATLAB code for a continuous rectangular pulse. The only difference, again, is that you use stem to plot the signal rather than plot. And the plot that is generated from this MATLAB code looks almost exactly like the plot that we just drew. The next elementary signal that we will be discussing is the unit impulse function, which is also known as the delta function. Now, the unit impulse is defined as delta of k equals u of k, the unit step, minus u of k minus 1, which equals 1 when k equals 0 and 0 when k does not equal 0. So the plot for this is very simple. So when k equals 0, the delta function will fire up to 1. And then everywhere else, for other values of k, delta of k equals 0. Now in the next video, which is on signal operations, you'll learn how to shift all of these elementary signals. Specifically for the unit impulse, you can shift it so it doesn't fire at 0. It could fire at 2 or 3 or -3. Just depends on what you want to do with it. And you can also make it fire up to, say, 2 or 3, or even a smaller value than that. But that will be in the next video on signal operations. Now the MATLAB code for the unit impulse is fairly simple. There's a built-in function in MATLAB called impulse, as you can see here on the left. And just like before, it's pretty similar to the MATLAB code if you were trying to plot a continuous signal. The only difference, again, is that you use stem to plot your discrete signal instead of using plot, which is used for continuous signals. And the plot that was generated from this MATLAB code can be seen on the right, and it looks exactly like the plot that we just made. Now let's talk about the next elementary signal, the sinusoidal function, or sine function for short. Sine function is defined as x of k equals the sine of omega naught k plus theta. Now for the discrete time sinusoidal function, omega naught is the discrete time, or dt, angular frequency. And omega naught equals 2 pi f naught, where f naught is the frequency in hertz. And in this instance, theta is the phase angle. So x of k can also be written as sine of 2 pi f naught k plus theta. Now to plot this function, it looks very similar to the continuous signal that's sinusoidal. However, the only difference is for discrete, we don't take the continuous signal, we just have certain points. So we're going to plot points from, on the positive side, we're going to go from 1/6 to a fourth, third to 1/2, and then on the negative side, we're going to do -1/6, -1/4, -1/3, and -1/2. So the amplitude for the discrete time sinusoidal function is still the same as the continuous sinusoidal function. So the amplitude is 1. So at k equals 0, x of k is going to be 0. And at k equals 1/6, x of k will be the square root of 3 over 2. And at k equals 1/4, it's going to shoot up to 1. At k equals 1/3, it will be the square root of 3 over 2 again. And then at 1/2, it will be 0 again. And on the negative side of the axis, at -1/6, x of k will be the negative square root of 3 over 2. Then at -1/4, x of k will be -1. Then at -1/3, x of k will be the negative square root of 3 over 2 again. And then at -1/2, x of k will go back down to 0 again. Now if I draw lines through the points like this, it looks just like a sine function would. So it has the same shape, we just don't draw it as a continuous signal. Discrete signals, you just take samples at certain points. Now the MATLAB code for a sinusoidal function is pretty similar to that of a continuous sinusoidal signal. The only difference, again, is that you use stem instead of plot, and also you have to specify the sample rate, and that will determine the number of points of data that you have. Now we will talk about the sinc function. The sinc function is defined as x of k equals the sinc of omega naught k. And this is also equal to the sine of pi omega naught k all over pi omega naught k, where omega naught equals 2 pi f naught, just like with the sinusoidal function, and f naught is the frequency in hertz. Now here is a basic plot of the sinc function with a frequency equal to 1. So the highest the sinc function can go is 1. So it's 1 at 0, and then after that, it has a very similar shape to that of a sine function. However, the larger or smaller you get in k, the smaller the amplitude gets, as you can see in this basic plot of the sinc function. Now, as you can see in the plot generated through MATLAB of the sinc function, you can see it a little bit more detailed, and you can see how much smaller the amplitude gets as you continue to get larger or smaller in k. And the MATLAB code is found right here on the left, and it is very similar to that of the sinusoidal function. The only difference is that you use sinc instead of sine. Now, as you can see in the MATLAB code for the sinc function, it's very similar to that of the sinusoidal function. The main difference is that you use sinc instead of sine, but most of the rest of the code for the sinc function is very similar to that of the sinusoidal function. And in this plot that is generated through MATLAB and through this code, you can get a better idea of the shape of the sinc function. And you can see how, as k grows larger, the amplitude starts to decrease. So the last elementary function that we will discuss is the exponential function. And the exponential function can be defined as x of k equals e to the sigma plus j omega naught k. And this can be written as e to the sigma k times e to the j omega naught k. And this can even be further written as e to the sigma k times the cosine of omega naught k plus j sine omega naught k. And here omega naught still equals 2 pi f naught, like in sinusoidal functions and also the sinc function. Now, there are two different cases when it comes to exponential functions. There's the case if the imaginary part equals 0. So if omega naught equals 0, then x of k equals e to the sigma k. However, if the real part equals 0, so if sigma equals 0, then x of k equals e to the j omega naught k, which means that x of k equals the cosine of omega naught k plus j sine omega naught k. Now, the plot for the exponential discrete signal is very difficult to do by hand, so I'm just going to show you the MATLAB plot so you can see it a little bit more detailed and a little bit neater and nicer than I can draw it. You can also compare it to the MATLAB code that has been provided to you. So on the left, you see the MATLAB code, and we have used the exponential function, and also we use the stem to plot it since it is a discrete signal. And on the right, you can see the exponential plot, and you can see for this one that as k becomes less, the amplitude of the signal decreases, and as k increases, the amplitude of the signal increases. And this will all depend on what values you have for sigma and for omega naught. Now that we have gone over all the different elementary discrete time signals, there will be a short MATLAB assignment. As you can see here, there are only two different questions. One involves a ramp function, and the other involves a sinusoidal function multiplied with the unit step function. Now, I have included a MATLAB supplement, which is basically all of the M files that you have seen in this video, and those files were used to generate all the plots that you've seen. Now, you are more than welcome to use this code to help you finish this MATLAB assignment. Now, in the next video, we will be discussing signal operations using all of the elementary signals that you learned in this video. I really hope that going over all of the different elementary signals has helped you and you have learned something from this video. Thank you very much.